So, dear ladies and gentlemen, welcome to the filtration workshop. Uh, we divided the filtration workshop in two parts. The first hour, or the first part, is about simulation of particulate flows through filters. And with filters, here we mean the whole filter with housing. And in the second part, or in the second hour of this filtration workshop, we're going to show the modeling and simulation of catalytic converters. So in general, the new features in Adedict module. My name is Mehdi Azimian. I'm responsible for the filtration business field of the master market company. And so the slides I prepared are just the step-by-step details of what we're going to do today. So whenever you have any problem or any question, or if you missed a point, you can also take a look at these slides, or if you want to do the uh, workshop later, you can also use these slides. But we're going to do a hands-on workshop today. So directly starting with the graphical user interface of Geodict. So, well, I'll change to Geodict here. So this is the graphical user interface of Geodict 2021. So here on the top, you find the list of modules from import of CT scans and CAD data up to structure generator modules like FiberGeo, PaperGeo, GrainGeo, and etc. And the analyze modules for defining the geometrical characteristics of your media. So we have FiberFind, GrainFind, PoroDict, and MadDict. And recently, the artificial intelligence based Geodict, which you can train neural networks and detect, for example, every single fiber or every single grain in your media and get more precise and detailed results. Under Predict, we have different modules for different applications. Of course, for filtration applications, you need FlowDict to compute the flow, uh, and you need FitAdict. So since 2021 version, uh, we merge FitAdict Media module and FitAdict Element module into one single module called FilterDict now. And it includes, as mentioned, the media element and complete filter, and also some predefined examples uh, or predefined cases for complete filter flow simulation and also cross-flow, flow, and filtration simulations. And of course, we have these export uh, geo modules to export your geometry, for example, or voxel structures to other well-known softwares. So let's start with the first part. So our aim is to first of all import the CAD geometry of a filter, and then uh, defining the settings of the simulation to prepare uh, the geometry to start filtration simulation. Um, First of all, the first step you need to do is to define or select an appropriate project folder. For this, you can here, as you can see the red mouse, you can right click on this and then select project folder. Uh, you can see here I already defined a project folder called Workshop Filtration M8 2020, but you can theoretically yeah, generate a new project folder, here new folder, and you can call it whatever you want. For example, here workshop filtration, and then you can actually choose this as your project folder. Yeah, I will reset this again to the one I already defined. All right. So the next step is to import the CAD geometry of your filter. As you can see under Import GeoCAD module, you can import STL files or OBJ files. So here, by click on Browse, uh, you can see these 5 different STL files that we provided for you. Uh, you can move these STL files into the folder that you defined, and then you can select all these STL files, which are the different separate parts of the filter. As you can see, the base plate, cap, inner support mesh, outer support mesh, and the pleat. And you select them all and open them together. Here you can see this is the user interface of the CAD import. Uh, the first thing is that you have to select the correct unit in which the CAD geometry is saved and exported. We know that it's millimeter. And then you can click here on suggest, and let's say we select 1000 voxels uh, along the longest axis. If we say okay, the other two axes, x and y, the number of voxels will be selected based on this maximum number in z direction in this case. So this is the number of voxels that we choose along the longest axis. As you can see, based on this number of voxels, the voxel length will be also selected. You see here these 5 different parts, and then we can theoretically click on import. This takes probably about 2 minutes time. In between, if you have any questions, we can answer them. Um, so again, one more important point is this is really important to select correctly. This is the unit of the CAD files. But even if you're not sure about this unit, you can select any other unit like meter or centimeter. And later, when you imported the STL files, you can also adjust the unit later by, for example, changing the voxel length, divide it to 10 or uh, multiply by 10 or 100 based on the unit you selected to get the correct dimensions of the filter that you see here. As you can see, with based on the voxel length and the number of voxels, you can see here also the length in X, in Y, and Z direction. So the filter is about 5.5 centimeter in Z direction and about 5 centimeter in X and Y. So quite a small oil filter, I would say. Yeah. Right. One more point, this right side unit is not that important like this one. This is only the unit that you see here, the value. So if you select here the meter, you see these dimensions all in meter. Uh, so this is only for visualization of the lenses and the sizes here. But this is the most important thing, that you have to select the right unit of the STL files. So we wait still a couple of moments so that our STL files would be imported into the Geodict user interface. And then afterwards, we have to also choose inlet and outlet domains and also define uh, porous material for pleat instead of solid. Because as you can see here, now every material is solid. which is also correct for these first four materials. But for the pleats, we have to change the solid into porous. And for the pleat, when you define porous media, you also have to define the permeability uh, of the porous media, which you whether get it from experiments, permeability experiments on flat sheet, or you could also run a flow simulation on a microstructure of your media uh, in an earlier simulation and then use the data later for here. So we don't need to see the triangulation. So yeah, so the geometry is now imported. This is the 2D view. We can change to 3D view, and you can here see the scale bar. We can keep the left mouse button and rotate this a bit. Uh, so here we can see the different parts with different colors, different material IDs from 0 to 5. Under structure tab, and then clip X, you can also visualize only a part of your filter to just see everything more clear. Uh, right. So as mentioned, uh, now every part except the fluid, which is oil, is solid. So we have to change the pleat material. This can be done here with this icon. Select constituted materials. Click on that. And then here you can click on material 5 and change it from solid to porous, and you have to select it as manual, and then you have to select oil as liquid flows through this porous media. Yeah? So we have here oil as the fluid, and here through the porous media you have to say or select the same fluid oil in porous media. The solid densities that you can see here, they would have no effect on the flow and filtration simulation, uh, the density of the solid parts. So here you don't need to define any density for the uh, solid material of the porous media, but it's very important to select the permeability. If it's isotropic, uh, you can write here the permeability that you already obtained from microstructure simulation, as I mentioned, or from uh, experiment on the flat sheets. Uh, if your permeability is isotropic, it means the same in every direction. If it's not, you can select anisotropic and select the different values in X, Y, and Z directions. We assume for this study isotropic permeability. The rest of the parameters are not necessary to edit or change. These are mainly important when you have mechanical simulations or uh, yeah, conduction simulations. So here you can set the temperature. Uh, so as long as we have here the correct material and correct permeability, we can click on run. We can see again and check this here. All right. So the next step is that beside the fluid uh, as ID0 and also the solid parts like the cover or the cap of the filter, the inner and outer support meshes, which are shown here with yellow color and blue color, and also here the base plate. We also have to define the inlet and outlet planes so that the flow can be injected through the filter and also later can be discharged uh, from the filter. So here the inlets are here on the sides, so the flow will pass through here the inlets, come here downwards, and then will passes through these purple pleat parts, and then the filtered liquid or oil will come up and then will discharge here from the outlet. So we have to define the inlet parts and outlet parts. For this, again, I deactivate the clip, or I just visualized um, complete filter. And again, I'll change from 3D view to 2D view and then select direction to Z. It means I will take a look at the filter from the top. And as mentioned, we have to choose here the inlet parts and here the outlet. For this, we have to here select edit selected voxels. You can also zoom a bit. No, that was fine. Um, yeah, all right. Here, edit selected voxels. So what we need is, first of all, to change the component mode from flood fill component to flood fill component plane. So plane, with that we define 2D planes for the inlet, and we also need to select a new material ID for the inlet. So up to 5 are already defined, so we select the 6, and then we start selecting points here. So 1, 2, and don't forget to also keep the STRG or control of your keyboard. Otherwise, when you select a second point, then the first point would be gone. So let's start from here again. 1, keeping the STRG or control. Second point, third, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Yeah, you can see here the left side we have 16 points. And now if you click on run, so all these 16 planes here will be set into material ID 6 with a uh, yeah, light blue color. You can again clear selection to remove those points. And then we have also to select the outlet plane, again as a flood fill component plane. Then assigning this to a new material ID 7. We select the point here somewhere in the middle and then click run. So we will have the outlet plane with a gray color here in the middle. We can again clear selection, close this, and we can check again the 3D view of the filter. Right, so you can see here inlet and outlet are added. Uh, so we have oil as the general uh, fluid, and we have oil which passes through the porous plate, and of course the oil which comes through the inlet and discharges from the outlet. So this fluid type should be the same overall. Again, we can take a look here uh, through the filter. Uh, the inner support mesh, as mentioned, with the yellow color, the outer support mesh with the blue color, the pleat itself with purple, and the inlet and outlet parts. All right, the geometry is now ready for filtration simulations or flow simulations. What you can do is before running a simulation, you can also save your structure as, for example, complete oil filter GDT, or I can call it again as a new name. I can save it so that you don't miss your the geometry and the material IDs that you defined. All right, great. So now the geometry is ready for filtration simulations. Um, Last year in the filtration workshop, I showed how to run pure flow simulation through the complete filter. Uh, this can be still found under FilterDict module under predefined, and there we have a complete filter flow that you can set the result file name, change the fluid type into the correct one, select the Stokes or Navier Stokes based on the Reynolds number, select the inlet and outlet boundary conditions, and so on. So this is what we did last year. And this is for when you have pure flow simulation without any particles. But let's say now we have also particles and we would like to simulate the filtration. This is now, this was also available last year, as we also did in the workshop, but now we have a new graphical user interface for the complete filter simulations, for particulate flow simulations. And for that, you can select on edit. So this is the first tab is the filter experiment, where you can select whether if you have a single pass or multi-pass test. So for this example, we select the constant flow rate single pass. Here you can select the concentration of the dust particles, the flow rate. For this example, we selected 10 liter per minute. And very important here is that you select the correct material ID for inlet and outlet. So as you can see here, the filter inflow area is now based on the complete area of the ID2, but we have to change this to ID6 for inlet, and for outflow or outlet, we have to change this to 7, right? As you can see, based on this selection, the filter inflow area is adjusted, and based on the flow rate and filter inflow area, the mean flow velocity at the inlet is computed. If you have a creeping flow where the Reynolds number is quite small, you can select Stokes-Brinkmann equation. Otherwise, if you have fast flow, you can use Navier-Stokes equation. For this example, we considered Stokes equation or Stokes-Brinkmann, where the Brinkmann term will be activated when we have also a porous layer in our geometry. So for example, in this case, the material 5 is a porous, and the Brinkmann term will be activated for that. Here at the left side, you can see the simulation stop criterion, and it means as soon as one of these selected criterions is reached, your simulation will be stopped. So in this case, whether after 100 seconds of filtration simulation or when the maximum pressure drop increase reach a value of 100,000 Pascal, the simulation will be stopped. You can also select all of them, but as mentioned, as soon as the first criterion is reached, the simulation will be stopped. All right. So everything is here done. The next point is the constituent materials, where you again check the fluid type uh, and also set the temperature. And based on this temperature uh, and also the fluid type, the density and viscosity will be adjusted. You can also check the permeability that you already defined here as 1e-11 for the porous part. And you can also see we have an unresolved case for the particle resolution, which in this case is automatically always as unresolved for the complete filter simulation, because you always have here quite big dimensions and considerably large voxel lenses, and you have particles which are considerably smaller than the voxel lens, and that's why uh, the particle resolution is selected as unresolved. When we have unresolved case, then we have to define some extra parameters called the local clogging and flow resistivity. Uh, and this should be defined for the pore voxels and also for the uh, porous voxels. So it means for the void voxels and also for the porous voxels. Uh, these are the parameters that are also discussed in my user meeting presentation. These parameters can be obtained from resolved simulations on the microstructure of your media. So here we need the parameters for the depth filtration. So everything happens through the porous media, and those for the void or pore voxels will define the cake filtration. So we adjust this based on the assumed values that we use for this simulation. All right. Okay. So the next step is the particles. This is also very important. Uh, under the first tab, positioning, uh, we don't need to change the random seed. This is only a statistical uh, number without any physical meaning. It just means you have some random positions for injection of particles. Um, particle multiplicity is important to activate when we have, as we can see later on the solver part, when we have, for example, let's say if we select 40 seconds time per each batch. So based on this time per batch and also the concentration of particles and the flow rate, um, this number of particles per patch will be computed. So as you can see here, we have about more than 84 millions of particles per each batch. And this is computationally very expensive if you want to track every single particle. And this multiplicity here will help that you track maximum, for example, 1,000 particles per each particle type. And then each particle will represent 100 or 1,000 particles, uh, which with its multiplication with this number, you get the real number of particles. So for this study, I selected the number of um, the number of maximum number of trajectories per type as 2000, and I also used the particle injection instead of batch start as continuous. Means it inject the particles continuously over all batches. All right. Um, yeah. So under the movement, here we can deactivate the Brownian motion. Uh, Brownian motion is has to be considered when we mainly deal with gas or air filtration and when the particles are small, so this effect becomes more important. But when we have oil as the liquid and quite bigger particles, so the Brownian motion can be neglected. And under interaction model, again, we can first of all set these maximum particle packing densities uh, that we chose already. Um, so for the material ID 0, pore, we select all particles passed. For inlet and outlet, also all particles passes. For the solid parts, it's impassable. And for porous part, we select the constant efficiency. And later, under size distribution tab, we have to select the fractional filtration efficiency for each particle sizes. So here we assume we have sand particles, we set the density, and we also select here the collision model as sieving overall. Uh, so cotton first touch is a very simplified model. Uh, it gives you quite good results when we have air or gas filtration with quite small particles, but more realistic model is a sieving or Hamakar, where the particle can bounce and lose a part of their kinetic energy when they hit a surface. Um, so the meanings of this number is that, uh, for example, if we have uh, a pore voxel, which at the beginning is empty, and it's filled later with particles, when the particles are located into this pore voxel, and 20 percentage of this pore voxel gets filled with the particles, then we consider this voxel as a full voxel. And then after that, when a new particle comes and hits this full voxel, then the collision model of sieving will be considered. And also for the rest here. So under size distribution, um, I would import the ISO A4 coarse particles. This can be found here under your normally the folder with which the geodict is installed. This is normally under your local disk, and then program files, mass to market here, the geodict 20 or 2021, and then here filterdict, and then here you can see a list of some of well-known particle size distributions that we have. So you can simply select A4 coarse, open, wait a couple of seconds, and then you would have the correct size distribution here. Right. So what else? We have to also define the restitution coefficient, and also the media thickness and the efficiency uh, of each particle size through the plate. So we have here particles from 1 micrometer up to about 125 micrometers. And we need for this fractional filtration efficiencies that this is also information or data that you could already find from result simulation on microstructure of the media. So to save a bit time, um, you can also here load the settings. Click on the load settings from file here at the bottom. And then select the GPS file or the settings file that I already saved. You can open this. Just click on yes. All right. So you can see the parameters are adjusted. So here you have restitution coefficient for different parts. I just assumed some values from 0.15 and then increased somehow up to a particle size of 7 micrometers, and for the rest I assumed just 0.5. So the restitution coefficient, it means the ratio of rebound velocity to the impact velocity of a particle when it hits a surface. Here I have the media thickness as 180 micrometers, and here you can see also the fractional filtration efficiencies starting from 0.3 or 30% from for 1 micrometer particle, and then increased up to 1 or 100% for very big particles. All right, this is also done under solver. Here you can keep the Lear solver as it is. Here you can select the time per batch. Here I chose 40. Here you can select the number of parallel processes. On the right side, you don't need to change this. This is only, you can change these settings when the convergence is a bit difficult to reach. You can set some relaxation factors and so on, but normally you don't need to change here. So under output, you can also decide if you want to keep all the results per each batch, or if you want to keep only the last batch. Uh, and if you also want to keep the trajectories of the particles and so on. This is the trajectories. If you want to keep all, this will need a lot of disk space, but this can be interesting when you want to make your video or an animation later. Okay, when you're done with all the settings that we talked about, you can click on OK. Please don't forget this, otherwise the settings or change that you made will be not considered. So click on OK always, and then the simulation is now ready. You can click on Run. We will not do it now because it takes a couple of hours, but I already did this simulation, and we can open the result files here on the top. You can see the open results icon, or you can also here select file and also from here open results. Yeah. So I already ran this simulation as mentioned, so you can open this. So first of all, you see the domain size, of course the same one, the voxel size, the date that I did the simulation. Here you see the green dot, it means this result file belongs to this structure. So if it was red, it means something is it doesn't belong to this, and you can load its structure. As you can see here, it says the simulation finished when the final time is reached. So we have here from batch 1 to batch 25. Um, so it means from time 0 up to time 1000. So I changed this time later to 1000 seconds based on the time per batch. When it's 40, then we have 40 times 20 uh, as 1000, so we have 20 batches. And you get detailed results for each batch. You get deposited dust in gram. You get the filtration efficiency by count and filtration efficiency by weight. Um, so by weight is of course you have a bigger number because uh, the bigger particles are of course filtered uh, filtered uh, considerably high, and that's why they have you get a bigger filtration efficiency by weight because of course the bigger particles have a bigger mass. Then we have a second table here, pressure drop. It means at the beginning you get the pressure drop. So this is the pressure drop of the clean filter, I would say. And then at each batch the pressure will increase gradually. So here after 25 batches we have uh, 6540 Pascal. And again here at the bottom, we have also filtration efficiencies per each particle type. So from particle type 1, which has a diameter of 1 micrometer, up to the last one, which has a diameter of 125 micrometer. And here you get also detailed results like the efficiency or fractional filtration efficiency of this particle at first batch. Uh, you can see this number of simulated particles from inflow, and this is the number of particles which are deposited and reach the outflow. Uh, so you get all this detailed information for each batch. All right. Under particle visualization, you can also visualize the particles. You can load the trajectories if you want to see also how the particle moves, or you can also uh, load the final positions. To accelerate a bit, I just load I would say every 20 particles. And then I can just simply say load particles. In the meantime, we can switch to the presentation again and go to the slide number 31. You can see some animations that you can uh, generate, uh, like how the particles at different batches will be injected from the inlet part, and then they pass through the pleats. They will be filtered, and some smaller particles they can which are not filtered, they will discharge here from the outlet. So particles are visualized here with a factor of 20 uh, to have a better visualization. So these are some videos or animations you can easily make with Geodict, uh, or some animations like this that you can first of all visualize your geometry, and then also show the streamlines or trajectories of the particles. All right. So Yeah, we are actually done with this part. Uh, this thing you see here is just loads the final position of particles, so that you can see the final positions of the particles at each batch. You can make animations and videos with that, but this needs its own, maybe its own training or workshop course. We're done actually with the first part. If it will be finished in a couple of seconds, I can show you some stuffs regarding the visualization. Yeah, it's done. So I'll go back to the. So what you can do is that first of all, you can see some particles probably here as I click over, but they are quite small. You can click on custom, edit custom, add selection, and then change the visualization, for example, to 10, and then also add another selection that you also want to show the previous batches. Again, visualization to 10. You can change the color of the particle from green to gray. Yeah, and then if we go from the first batch and then click further, you can see the final position of the particles, uh, which are filtered through the uh, media of the pleat and later as a cake on on the the pleats. All right, that was the first part from my side. Thank you very much for your attention, and we will probably have a bit time for questions, and then we will shift to the next uh, workshop part. Thank you very much, and goodbye.